Alright, today we're going to do a quick video on 8.1 and 8.2 rational functions notes. This is just if you want to get a quick head start for class on rational functions, which I think is the next unit you guys will be learning. So starting off, a rational function is a function that looks like a ratio, ratio or fraction of two polynomials. So for example, x minus 1 is not a rational function, but x minus 1 over x plus 1 is, because you got your two polynomials and it's a ratio because there's a fraction bar. Alright, and I'm just going to keep it there. So what if we need to graph these? We'll be graphing a lot of rational functions in 3+. So you graph them using something called vertical asymptotes. Basically where the graph will never touch it. Horizontal asymptotes, which is the behavior of the graph as x goes to infinity. Slant asymptotes, which is part of horizontal asymptotes. It's a asymptote without a slant. It's a value that x reaches. Holes, which are holes in the function, so it's just like an undefined point. X-intercepts and y-intercepts. So those are the main things you want to check for to graph a function. To graph a function correctly. And other than that, if you have any other parts of the graph, you don't really need to find them, because this is usually generally considered enough of a graph of the rational function, because you don't need to find every single value. All right, so what are vertical asymptotes? So vertical asymptotes are when the denominator is 0. So for example, of 1 over x minus 1, the vertical asymptote of this function would be the line x equals 1. So that would look something like this. And it's this line right here. That is our vertical asymptote. And basically, the line of this graph will never touch it. But I'm not sure if that's what the function looks like. It might be on this side, but that doesn't matter too much. I'm just highlighting the fact that there is a vertical asymptote there. All right. So next we have horizontal asymptotes. We did some of this last year in 2+, but just to refresh your memory, if the top one is bigger than the bottom one by any degree, so it could be 1, so it could be x squared on the top plus 1, and then like x plus 1 on the bottom, it's still bigger. The degree is still bigger. There's a 1 in there. If the degree is bigger, the horizontal asymptote does not exist, because it will be going to infinity. If you think about it, the top of the function as x gets really, really big will become much bigger. So if you have like x squared on top again as the example, in x on top, if this is like some huge number, it will completely dominate the function. So even if it's a same big number on the bottom, the top will be much, much, much bigger. So therefore, this function goes to infinity. So f of x goes to infinity or negative infinity, depending on which side you are going to. You know what? Quick note: if we have some acronyms, VA, vertical asymptote. Hold on, I should probably write this over here. Vertical asymptote is VA, horizontal asymptote is HA, and slant asymptote is going to be SA down here. And I'm just going to use those from now on because I don't want to write out asymptote every time. So horizontal asymptote, it does not exist if the top is bigger than the bottom. But what if the bottom is bigger? Well, let's think about it again. If we have x plus 1 on top this time and x squared plus 1 on the bottom, this number becomes much, much bigger, right? And this is like just a smaller number in comparison when x is very, very big. So if you have a big number on the bottom of a fraction compared to a small number on top, this goes to 0, right? As x gets really, really big. So the horizontal asymptote is the line y equals 0. And it's important about horizontal asymptotes that even if it's a horizontal asymptote, the graph can cross it. It is simply the behavior of the graph as x gets really, really big. So we can have some sort of graph that looks like this, where it crosses the line y equals 0. But as it goes out to infinity in these two directions, it gets closer and closer to the line y equals 0, but never touches it. It's important to know that on these extreme ends, horizontal asymptotes are not touched, and for vertical asymptotes, they are never touched no matter what. But, however, what if these are equal? So let's think about this one more time. Let's say we have 2x squared plus 1 over x squared plus 1. The domain, let me use a highlighter. The domain up here is the same. So what do we do now? Well, in this case, if x gets really big and x gets really big, the top and bottom follow each other. So you just got to remember that the only thing you have to figure out is you take the leading coefficient of the top and divide it by the bottom. So it's going to be 2 divided by 1 equals 2. So our line y equals 2 is our horizontal asymptote. When they're equal, the good rule of thumb is just remember, divide the leading coefficients. All right. Next, last one, holes. Holes are when factors cancel out of the function. So if you have x minus 1, x plus 1, and you have x minus 1 on the bottom, and then like x plus 3, we have this canceling out, and it becomes x plus 1 over x plus 3, right? But since this is our new function, we just graph this. However, we need to remember that in the original one, we're not allowed to have x equals 1. So no matter if our graph is just for example, if our graph looks like this and it had an x equals 1 cancel out, there should be a hole right there at x equals 1, because in the original one, we're not allowed to have x equals 1. So that's always something good to remember, or actually it's required when you're graphing a rational function. All right, now there's only one more possible asymptote that we need to take into consideration, which is called slant asymptotes. Okay, this is a little interesting of a rule, and I don't really know how to explain it, but if you just remember it, if the top, which we remember defined as p of x, is greater in degree than q of x by a single degree, so by one exponent, single degree. For example, we have x to the 4th plus 1 over x to the 3rd plus 1. There is a slant asymptote. And it's very important to emphasize the fact that it must be 1 degree. If it's bigger, then there is no slant asymptote. It just goes to infinity on either ends, or negative infinity, depending on how the function behaves. So what is a slant asymptote? A slant asymptote is just like any other, it's just like a horizontal asymptote. As x goes to infinity, it behaves like this line. So like, say this is our asymptote. That means our function will go to this as it goes out to infinity. Like there. Oh, actually, that is not a correct drawing. My apologies. There we go. This one. Okay. As you can see, these ends, this end and this end, as x goes out towards infinity, start touching, or actually, my apologies again, as it goes to infinity, it should not touch. It will be very, very close to this line. It will start behaving like that line. So now the question is, how do we find this slant asymptote? And the answer is we use long division. And then after using this long division, we just take the equation that comes out, and that is the slant asymptote. Oh, and it should be important to note that actually no. This is fine. This works. We use long division. That's right. Okay, so let's use our example once again. So we have x4 x to the third plus 1. So there are a few terms missing in the middle, and you know what, to make this easier, we're just going to use a single degree starting at the bottom. So we have x plus 1 and x squared plus 1. This will be slightly easier. So x squared plus 1 plus 0x plus 1, like this, and then x plus 1. So you just set up the equation, instead of in this ratio form, you set it up in this long division form, and then you perform the long division. So if we perform the long division, what times x gives us x squared, and that's obviously just x. So we do subtract x squared plus x, and since it's subtracting, it becomes negative x here. Bring down the plus 1. What times x gives us negative 1? I mean negative x, obviously negative 1. So, and anything after this we don't need to worry about, because once again, as it goes bigger and bigger, the constant becomes negligible, remember? But let's just see what happens if we continue with this. And this gives us 2. And this remainder doesn't matter, because remember, usually we would put a remainder here if we're actually finishing the long division. But as x gets really big, this bottom becomes super big compared to the constantly small top. So this just goes down to 0 actually when x becomes infinity. So the only thing that matters here is this function right here. So this gives us our slant asymptote, which we take directly, and it equals the line y equals x minus 1. And y equals x minus 1 looks something like this. So in this function that we just had, as it goes to infinity, the two ends will start getting really close to this function. All right, so that's slant asymptotes, and that's actually all we needed to learn that we didn't know already how to find. Because before, we knew how to find x-intercepts and y-intercepts. You just set one of the sides to 0. So now we found all our asymptotes and our holes. So this is now enough to graph any rational function you see. So let's just take this example right here. It says f of x equals x squared plus 7x plus 6 divided by x minus 3. So this is going to be a slant asymptote, as you see, because we have our 2, which is slightly bigger than which is 1 degree bigger than the x to the 1 on the bottom. So let's set up our nice long division right here. Oh, that is not a division sign, that is a radical sign, like this. Now, once again, what times x gets us x squared, and that's just x. So we have x squared minus 3x. And then these cancel, so it's like this. What times x gives us 10x? It's 10, so we do positive 10. And once we get to the end, we don't have to do any of this at the end anymore, so we just stop here. Our slant asymptote is y equals x plus 10. So the remainder is negligible. There we go, and that's all we need to find, because this is just a practice with slant asymptotes. I am going to leave the second example to you guys, so that's some just good practice for you guys. And let's move on. So next is guidelines for graphing. There are a few main guidelines. The first one is you always factor. Factor slash simplify. The expression. This helps you find holes. So when you cancel something else, when you cancel it out, you get a hole, and zeros. Because remember, whenever the top equals 0, you know that that's a 0. So if we, say we have our function x squared plus 3x plus 2 over x squared minus 1, we would always want to change this to x plus 1 times x plus 2 over x minus 1 and x plus 1. And then this lets us cancel out to get a hole at x equals negative 1. and then it gives us x plus 2 over x minus 1, which tells us there's a 0 at x equals negative 2. So these are really important. So the first step is very important. So the second one, we have our second guideline, which is going to be find VAs and HA or slant asymptote. So there could be multiple vertical asymptotes in a function. However, there is always only going to be one horizontal asymptote or slant asymptote or neither. None. I'm just going to say none. Or none. Now, number 3. Oh, and remember, vertical asymptotes is just finding when the bottom is 0. So we know there's a vertical asymptote on this example again at x equals 1. This is VA. This is x-intercept. This is a hole. I know, it's a lot to keep track of. Then you want to draw, so you start with your vertical asymptote. You always just use a dotted line. And horizontal slash slant asymptotes is also with the dotted line, and it should give you some boundaries. Then for 4, our last one, use values close to vertical asymptote to see if it goes to positive infinity or negative infinity. And you will see this in use in this next example. So obviously I'll go through all these steps, and yeah, let's do it. We'll just take a look at these ones, which ones are good. We will do number 2, and let's also do number 1. Yeah, I'll just do 1 and 2, and then 3 and 4 you can do on your own. If you have questions, you can ask me or check the solutions online. All right, so first step, can we factor, simplify, or divide anything out? No. So our first step, step 1, nothing for us. All right, so step 2, what was our step 2? Find vertical asymptotes and horizontal asymptotes. So, we have a vertical asymptote right here. So step 2, we have a vertical asymptote at x equals negative 1. And let's see if we can find a horizontal asymptote. As you can see, the degree is the same for the top and the bottom. So we need to divide by the leading coefficients. So HA is going to be y equals 3. All right, next step is to start the graphing process. So let's just graph this right here. It doesn't have to be too perfect. And then your little arrows, and always do the check mark things, the grid lines. It is always more helpful, and usually it's in ones, but if like something is just scale is too big, you can always adjust the scale of these, but make sure it's consistent. First step, where is our horizontal asymptote? We have it right here at y equals 3. And where is our horizontal asymptote? We have one at x equals negative 1, so that's right here. This is the line x equals negative 1. Then, what's our last step? We have to use values near the vertical asymptote to see if it goes to positive or negative infinity. So, what's a good one? Well, obviously the best one here is going to be x equals 0 because it's right here. So if x equals 0, what does this equal? And as you can see, if it's 0, we just get 9. So I'm just going to do a point up here I'm going to call 9, and we're going to know it looks like this. And this is just going to be 9. Next, we have to find the other side. So the best value to use is just going to be negative 2 here. So we have 3, negative 2, plus 3 over negative 2 plus 1. So we have 3 times, the inside is 1 over negative 1, which is equal to negative 3. So negative 3 is down here, 1, 2, 3. So then we can tell that this one's going to go like this. And then this is our finished graph. This graph counts as fully drawn out. This is all you need. All right, let's move on to number 2. So step 1, factor. And it looks like we can in this case. So this is going to be equal to 5 times x plus 3, x minus 2. And this one's going to be 3 times x minus 2, x minus 1. And looks like we can cancel something. So we're going to have a whole, whole at x equals 2. And let's see, we have a 0 here and a horizontal asymptote. Actually, vertical asymptote, that is my bad. So we have x-intercept at, let's see, negative 3, and then vertical asymptote at x equals 1. And then obviously we have the same thing going on here where our degree is the same. So we're just gonna, oh, and they conveniently have the leading coefficients outside of the two functions. So our horizontal asymptote is going to be 5 over 3. And always make sure to have the x equals or y equals because asymptotes are lines. They are not simply values. All right, so we can begin our graphing process if we just draw our x and y and x-axis, axes. And as we can see, we have our vertical asymptote at x equals 1. We're going to use a dotted line for that. And then a horizontal asymptote at 5 divided by 3. So that's right under 2. So we have 1 like this, 1. And then if we want to find it when x is 0, so a good value to check is always x equals 0. And in this case, it appears that if x is 0, then we get we have x is 0, we have 5 times 3 over 3, right? Yes. Okay. So we are going to do this like this. This is equal to negative 5. So that is going to be 1, 2, 3, 4, 5 here. That tells us that this function is going to be on here on this side. And usually with these functions, you can assume it's going to be the one that's like here in this quadrant, but you can't always assume that. So make sure to check. So let's just check 2. If x is equal to 2, we're going to get 5 times 5 over 3, which is equal to 25 over 3. Yeah, 25 over 3. Nice. So this value up here, we're just going to draw a little hole. Actually, I'll mention that later. But if we have it like this, and we have a 25 over 3, right? We're done, right? Actually, no. If you remember, we have a hole at x equals 2. So this has to be an open circle at x equals 2. And make sure to properly note that this is at this value, like this. Like so. Or you can put it over here, and that will work as well. But you just got to make sure you have that hole drawn. But that is our first 2 examples. I will leave the next 2 for you guys. Oh, actually, next few for you guys to just work out on your own. And let's move on to number 7. Number 7 here is write the equation of a rational function that has vertical asymptotes at x equals 0, x equals 5 over 2, a horizontal asymptote at here, and then these zeros and these holes. All right, so the easiest one by far to start with is the whole zeros and asymptotes. So 0 is at these values, so we're going to have it x minus 1 for the 1, and then x plus 4 for the negative 4. Then what do we want to be able to cancel out? We want this x minus 9 to cancel out, because we have a whole at 9, and x plus 5 to cancel out. And since it cancels out, so we put that on the bottom as well. Then we want these two vertical asymptotes, so we have an x equals 0, so we're multiplying by x in there, and then we have an x equals 5 over 2, so we're going to do an x minus 5 over 2. Nice. All right, we're done, right? No, we have our horizontal asymptote. And let's count our degrees. 1, 2, 3, 4. 1, 2, 3, 4. So the degrees are the same, so we can just add a negative 3 on top, because remember, it's just 1 in the front. Negative 3 divided by 1 is negative 3, which gives our vertical asymptote. So this is good here. This is good here and here. This is good here, 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 and here. And then these two are good here and here. These two. Perfect. There's one last graphing problem, and I will do it because it is slightly different. All right, step 1, factor everything out. X squared plus minus 4 is equal to x minus 2 times x plus 2. X plus 2 is on the bottom. These cancel out, which gives us x minus 2. All right, so let's just draw it. And let's see. All right, 1, 2, right here. And there we go, we're done, right? Well, actually not, because remember, we have this hole at negative 2, so 1, 2, negative 2, and hole. Now we're done. So that would be a complete graph as well. All right, thanks for watching. I'll probably make more notes soon on other stuff if you want, and if you ever need help, you can always just ask me. You can send me a message, and I will try to answer as fast as I can. As always, if you guys want me to make more note videos, I will continue making them. So yeah, thanks for watching. Goodbye.